Okay, hello guys. Welcome. We're going to go over page 17 of your guided chemistry notes. And this is over intermolecular forces, and we abbreviate it to IMF. So whenever you see IMF, it's talking about intermolecular forces. So what exactly are intermolecular forces? We kind of briefly mentioned them on a different page of our notes. I want to say maybe page 11 perhaps, but we're going to go into more depth right now. Okay, so what's the difference between intermolecular forces and intramolecular forces? Okay, well, intermolecular forces are between molecules, whereas intramolecular forces are within molecules. Okay, intramolecular forces are also just known as bonds. So all the bonds that we've been talking about, ionic covalent bonds, all of that, these are examples of intramolecular forces. We don't really use this term very often. Okay, we just call them bonds. Okay, but when we're talking about intermolecular forces, which is what we're talking about today, we're talking about the forces that exist between the molecules themselves. So for example, right here, you see a hydrogen bonded to a chlorine, okay? But, so this would be an inter or a bond between those two, and how they interact, how the molecules themselves interact with each other, that's called an intermolecular force, intermolecular force, okay, IMF. All right, you see the intermolecular forces are breaking here. Okay, so let me just draw another little picture up here. So if we're talking about water, I'm going to draw a water molecule, and I'm going to draw another water molecule like this. Okay, and I'm going to see these things are the intramolecular forces, okay, or the bonds, aka bonds. Okay, whereas the interaction between these molecules, I'm going to put a dotted line, the interaction between this molecule and between this molecule, that interaction, this would be an intermolecular force. Okay, I won't write out the whole thing, but you get the idea. Okay, an intermolecular force. And this is what we're talking about today, this attraction between the molecules themselves. Okay, which type of force is stronger? Bonds are stronger. Okay, so these guys are stronger. Bonds are stronger, or intra. Those ones are stronger. Okay, so why are intermolecular forces, and remember, when we put IMF, we're assuming that we're referring to the inter. Why are IMFs important? If bonds are stronger, why are IMFs important? They are important because they determine a lot of properties, like melting point, boiling point, and solubility. Okay? And you'll see this phrase a lot in chemistry and sometimes in biology too. It says like dissolves like. So that basically, and we've seen this before in our notes, it means that polar things dissolve polar things. Polar things dissolve polar things. And etc. Non-polar things dissolve non-polar things. So this is the reason why oil and water don't mix, because water is polar and oil is non-polar. So like dissolves like, things that are alike dissolve in each other. Okay? Okay, so let's talk, now that we know what an intermolecular force is, there are different types. And we are going to talk about 3 types of intermolecular forces today. The 3 types we're going to talk about are first, London dispersion forces, second, dipole-dipole interactions, third back here, it's hydrogen bonding. So those are the 3 types of intermolecular forces we're going to talk about in 8th grade chemistry, okay? The first one is called London dispersion forces. These are the weakest of all the intermolecular forces. They are present in all covalent substances, whether it's polar or nonpolar. Okay, they're weak. Okay, everything has London dispersion forces. The more massive the molecule, the stronger the London dispersion forces. So basically, the more, it really has to do with how many electrons the molecule has. If it's a bigger atom with more electrons, because really what's going on in London dispersion forces is as molecules move around, think of it as if you were to take a glass of water and you were to move it around, the water would kind of swish to both sides of the glass, right, as you were to move it. That's kind of almost the way you can think about what's happening to the electrons here. As atoms are moving around, their electrons are kind of swinging from one side to the other. So at any given point, there's a slight attraction between, because the electrons might be more on this side than on that side. So there's going to be like one moment where the electrons are going to be further on one side, making it have like kind of a pseudo-negative charge, attracting it to maybe the pseudo-positive charge of another molecule. So it's a very weak interaction, but it does exist, okay? It's also sometimes called instantaneous dipole interaction. Basically, it just means that at any instant, there could be a brief momentary dipole, which might kind of attract it to another brief momentary dipole. Okay, but what you guys just need to understand is that these are the weakest of all the intermolecular forces. They're present in all covalent substances, okay? And the bigger your molecule, the stronger the London dispersion forces are going to be. London dispersion forces is LDF. So if you see LDF, that's what that is, London dispersion forces. Okay, so if you look at this little picture here, I love this picture because it shows you've got an intramolecular nonpolar covalent bonding. So this is a bond. Okay, and then you have these interactions, these London dispersion forces, these intermolecular forces, these IMFs, that are kind of attracting these chlorine molecules together. Okay, they're kind of attracted to each other. It's not attracted enough to be considered a bond, but it's an attraction. Okay. Okay, so practice. Which of the following has stronger London dispersion forces? Bromine or chlorine? Which one do you think would have stronger London dispersion forces? Bromine or chlorine? Well, let's look at bromine and chlorine. Bromine is bigger than chlorine. If we're talking atomic radius-wise, it's bigger. It also just has more electrons total, and it has a larger mass. So all things considered, bromine is bigger. So because bromine is bigger, okay, it's going to have stronger London dispersion forces. We say because it's bigger. Because it's bigger. Sorry, it's bigger. Okay, which of the following would you expect to have a higher boiling point, bromine or chlorine? Okay, well, if it has stronger London dispersion forces or stronger intermolecular forces, it's going to have a higher boiling point. So bromine would have a higher boiling point. Okay, and that's because it has stronger intermolecular forces or stronger London dispersion forces. Okay, because remember, a London dispersion force is a type of intermolecular force. Okay. Okay. So as your intermolecular forces get stronger, as these get stronger, your melting point goes up, your boiling point goes up. Okay. Okay. Second one we're going to talk about are dipole-dipole interactions. Dipole-dipole interactions. So these are only present between polar molecules. Only present between polar molecules. So good thing we learned about last time. We learned about how to determine if a molecule is polar or not. Okay, it only happens in polar molecules. Okay, dipole-dipole interactions are strong. They're definitely stronger than our London dispersion forces. Okay, and this is basically like the same reason why London dispersion forces exist, meaning those electrons kind of, when there's more electrons on one side of the molecule than there are on the other side of the molecule. Remember, we talked about how it can create a dipole or a little pseudo-positive charge on one end and a pseudo-negative charge on the other end. And those partial positive and partial negative charges are attracted to each other. And in a polar molecule, it's not just an instantaneous dipole that exists like in London dispersion forces. There's always a dipole there because you have a difference in electronegativities. So like in this molecule, for example, chlorine is much more electronegative than hydrogen, so it hogs the electrons more often, giving it a partial negative charge, and it's always going to have that partial negative charge. Hydrogen's always going to have a partial positive charge, so they're going to be attracted to each other. Okay, they're going to be attracted to each other. Now, attraction is not strong enough to be considered a bond. It's considered an intermolecular force. It's considered a dipole-dipole interaction. Okay. Okay. So let's do a practice problem. It says rank the following in order of increasing intermolecular forces and explain your answer. Okay, so we have three different things here. We need to figure out which one has the strongest intermolecular forces. Well, we know that these are stronger than these, right? So these only happen in polar molecules. So we need to figure out, okay, are any of these polar? That's what we need to ask ourselves. Okay, so let's draw out our Lewis dot structure, and I'll just do it a little quickly, just in the interest of time, instead of showing all my math and everything. Okay, so that's what F2 looks like. NH3, if you were to do the math, you would find that it has 8 valence electrons. So it's going to look like this. And I2, we have an iodine and another iodine. Okay. And I'm going to filter out tests. So if you want to figure out if something's polar or not, you really need to draw out its Lewis dot structure so that you can figure out if it's polar or not, and then you can figure out if it's going to have dipole-dipole interactions or whether it's just going to have London dispersion forces. Okay. Okay. So let's see. Is this polar? No, this is not polar. This is non-polar. Non-polar, because it's symmetrical. Okay, it's symmetrical. It's the same on both sides. And I know there's no central atom to look at, but if it's a diatonic element, it's always going to be, and it's symmetrical. So just like something bonded to itself, like an I and an I, or an F and an F, it's always going to be nonpolar because no one's hogging the electrons because they're equally matched. Okay. This one, however, is polar, and we know it's polar based on our notes last week that whenever you have a lone pair on a central atom, it automatically makes it a polar molecule. Okay. So because this one's polar, this one's the only one that can do dipole-dipole interaction. So that's going to be our strongest. So if we're making them in order of increasing IMFs, okay, so that would mean our weakest needs to be here, weakest, and then strongest needs to be over here. Well, we just figured out that NH3 is going to be our strongest, right? Okay, so now between these two, we need to figure out which one's weaker. Well, neither of them can do dipole-dipole. They both do London dispersion forces. So between the two of these that do London dispersion forces, how do we determine which one's stronger? Well, we said the more mass of the molecule, the stronger the intermolecular force is. Well, because iodine is bigger on the periodic table than fluorine, iodine is going to be the next strongest. So iodine is going to be right here. And then fluorine will be our weakest. Okay? So this would be the order right here. Right here. Weakest to strongest. Okay? Okay. That's how you do a problem like that. Let's flip over. The last one we're going to talk about in terms of types of intermolecular forces is called hydrogen bonding. And this is something, I don't know if you've talked about it in biology or if you will talk about it in biology, but it's very important in biology. If you go on to take AP biology, you'll absolutely need to know about hydrogen bonding, and AP chemistry as well, of course. Okay? So hydrogen bonding is a special type of dipole-dipole interaction. It's like a super duper strong type of dipole-dipole interaction. And I want to point something out that's very, 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 very important. It's not really a bond. It is a misnomer, okay? Hydrogen bonding is not really bonding. It's not a bond. It's just a nickname because it's such a strong intermolecular force that they nicknamed it hydrogen bonding, but it's not actually a bond. And this is what's tough for students to realize is that hydrogen bonding is not actual. It's not talking about the bonds between hydrogens. It's not talking about that. So hydrogen bonding is the interaction that happens between the molecules. It's not actually bonding. Okay, This is not hydrogen bonding. This is just a bond. This is just a polar covalent bond, okay? This is the hydrogen bonding. Okay, this is the hydrogen bonding, and it's just such a strong intermolecular force that they nicknamed it hydrogen bonding, but it's not actually a bond. Okay, I know it's confusing, but that's the way it is. So it's the strongest. It's the strongest of all the intermolecular forces we're learning about this year. It's even stronger than dipole-dipole because it's almost like a type of dipole-dipole that's like a really, really, really strong type of dipole-dipole. Okay. So it's only present in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. Now, the hydrogen bonded to the fluorine, oxygen, and nitrogen, that is not the hydrogen bond. Again, this is not the hydrogen bond. The hydrogen bonding only occurs when you have a molecule in which hydrogen is bonded to one of those. And then this hydrogen bonding can occur. And the reason why is because these are very electronegative elements, and they're so electronegative that they hog the electrons so much versus hydrogen, which is not very electronegative, that it creates like a super duper dipole, okay? A super duper partial negative and positive charge. And that's why it's between these ones, okay? This is why, so hydrogen bonding exists in water. That's what it's famous for. And it exists, and it causes water to have a high boiling point and high melting point compared to most liquid molecules. The more hydrogen bonds that you have, the stronger your intermolecular forces, okay? So that's water versus ethanol. So if you were to take water and ethanol, if we weren't in quarantine, I would take some, we would do a lab called drops on a penny, and I would show you that I would see how many drops of water I could fit on a penny and how many drops of ethanol I could fit on a penny, and you would see that there's more drops of water that would fit on a penny than ethanol, and that's because water can form a stronger hydrogen bonding because it can form hydrogen bonds from here and from here and from here, whereas ethanol, I'll show you guys what ethanol looks like. It's kind of a complicated organic molecule. It's kind of big. This is what ethanol looks like. So ethanol is also polar, and it can also do hydrogen bonding, but here's its partial negative side and here's its partial positive side. It can only really do hydrogen bonding with other molecules from here and from here, okay? And it's a little bit more big and cumbersome, whereas water, it can do hydrogen bonding from here and from here and from here. So it has more areas it can do hydrogen bonding. So that's why it has stronger intermolecular forces than ethanol. So let's do practice. It says identify the following if the following molecules are capable of hydrogen bonding. Okay, so does it have hydrogen in it? No, so it cannot. Nope. This one has hydrogen in it. Is the hydrogen attached to one of these? Yes, it's attached to fluorine. So yep, that one can do hydrogen bonding. Does this have hydrogen in it? It does have hydrogen in it. But is the hydrogen attached to fluorine, oxygen, or nitrogen? No, it's not. So this one cannot do hydrogen bonding. This one has hydrogen and it's attached to a nitrogen. So yep, this one can do hydrogen bonding. This one can also do hydrogen bonding because the way that would look is you'd have a carbon with 3 hydrogens around it with an oxygen and a hydrogen. So that's how this one would look. Because the hydrogen is bonded to the oxygen, that one can do hydrogen bonding. And this one would look like a carbon with 3 fluorines, fluorine, 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 and then hydrogen. It has hydrogen and it has fluorine, but is the hydrogen bonded to the fluorine? No, it's not. So this one cannot do hydrogen bonding. Okay? Okay, cool. So the 3 types of intermolecular forces that we just talked about, hydrogen bonding, dipole-dipole, and London dispersion forces, these types of intermolecular forces are known as, you might have heard this in biology, van der Waals forces. Van der Waals forces. Van der Waals forces. And they happen only in covalent substances. So everything we just talked about only happens in covalent substances. There are also some intermolecular forces. So these are because they happen in covalent substances, these are the ones you talk about in biology a lot, because pretty much everything in your body, for the most part, is a covalent substance. Okay, so that's why we talk about these in biology as van der Waals forces. However, there are intermolecular forces called ion dipole forces that happen between ionic compounds and polar covalent compounds. These ion dipole forces our interactions are stronger than van der Waals. They're even stronger than all of the ones we just talked about, but we're not going to cover them this year. Okay, I just wanted to point that out. So again, if you want to take AP chemistry and you're like, no, hydrogen bonding is the strongest. Well, it is the strongest amongst the van der Waals forces, but there are ion dipole forces, which could even be stronger than hydrogen bonding. Okay. Okay, let's talk about a few key terms real fast. Some of these you may or may not see in biology. First one's cohesion. It's just when molecules of a substance are attracted to each other. Okay, when molecules of a substance are attracted to each other. So that's why if you like put a drop of water on a table and another drop of water on a table really, really close to it, sometimes they suck together and make one big drop of water. It's because they're attracted to each other. Okay, adhesion, and this is what causes surface tension in a swimming pool. If you go jump into a swimming pool from high dive, it's going to hurt when you hit the water, right? That's because the water molecules are attracted to each other, almost forming like a barrier on the top of the water. Adhesion is the molecules of one substance being attracted to the molecules of another substance. So when I think of adhesion, I think of like remember we talked about a meniscus. So when you pour water into a graduated cylinder, the water kind of will hug the sides of the graduated cylinder a little bit. That's because of adhesion. The water molecules are a little bit attracted to the side of the glass. Okay, surface tension. Again, we just talked about surface tension. So it's caused by the attraction between the molecules, the cohesion between the molecules. It's like surface tension of water. You have to break through the surface tension of the swimming pool when you get in, right? And if you do a belly flop, it can hurt, right? So that's surface tension. Viscosity is a liquid's resistance to flow. So if something is very viscous, think of like honey or syrup. Those are very viscous because they flow very slowly, okay? So when they have really strong intermolecular forces like honey, oh, there you go, honey versus water, they're going to flow a lot slower because they're very attracted to each other. Okay, and last one's capillary action. Capillary action it describes the spontaneous flow of a liquid into a narrow tube or porous material. This movement does not require the force of gravity to occur. In fact, it often acts in opposition to gravity. Okay, so basically it means like it's when your adhesion is stronger than your cohesion. So an example is water moving up paper. So when we talked about chromatography, I showed you guys an example of if you you dip a paper towel into the water will creep up the paper towel against gravity, and that's because the water molecules are attracted to the paper towel. This is how plants draw water into their leaves from out of the ground. This is how tear ducts work, okay? So that's capillary action. Okay, and here's a little cartoon I think is cute. Cohesion, it's two molecules attracted to, themselves basically. Adhesion is attracted to something else, and for surface tension this is why skeeter bugs can kind of walk on top of the water because the water molecules are attracted to each other, creating almost like a barrier on the top of the water. Okay? Now, I need you guys to go watch the video. If you just type this in your YouTube, Liquids Crash Course Chemistry number 26, that will give you guys crash course video. Super fun, super interesting. Watch it and write 3 facts that prove to me that you actually watched the entire video. Okay? Alrighty. Thank you so much.